The blood of batteries. What is electrolyte? Did you know? Lithium batteries have blood too. It's called the electrolyte. Electrolyte is called the blood of lithium batteries. It transports ions and conducts current inside the battery, directly affecting energy density, safety, cycle life, and rate performance. A good electrolyte must not only conduct ions but also remain stable, safe, and non-toxic. It wets the electrodes and provides an interface for reactions, supporting the entire battery system. Without electrolyte, a lithium battery simply cannot work. 3 key ingredients that define battery performance. Electrolyte has 3 key ingredients. Solvent for conductivity and temperature range. Lithium salt provides lithium ions. LiPF is the mainstream choice. Additives are tiny but boost cycle life, rate, and safety. Together, they make batteries stronger, longer lasting, and safer. What makes a good lithium battery solvent? High dielectric constant, low viscosity, stable with battery materials, works well in heat and cold, easy to wet electrodes, safe, cheap, easy to make. High dielectric constant, better lithium salt dissolution and dissociation capability, low viscosity, lower ion migration resistance and improved ionic conductivity. Cyclic carbonates have a very high dielectric constant, but also high viscosity. Linear carbonates have a lower dielectric constant, but also lower viscosity. To meet various requirements such as working temperature range and ionic conductivity, a mixture of high dielectric cyclic carbonates and low viscosity linear carbonates is typically used. This is recommended applications of common solvents. The lithium salt in the electrolyte is what truly enables lithium ions to flow. Part 1. Why lithium salts matter. Lithium salts dissolve in the electrolyte, dissociate, and release lithium ions. These lithium ions move back and forth to create current powering your battery. No lithium salts equals no lithium-ion battery. What makes a good lithium salt? Easily dissolves and dissociates. High conductivity, good thermal and chemical stability, environmentally friendly decomposition products, cost-effective and scalable for mass production. Part 2. Why LiPF is the industry standard. Lithium hexafluorophosphate, the industry's mainstream choice. Not perfect, but the most balanced option so far. High conductivity, excellent electrochemical stability, passivates aluminum to prevent corrosion, compatible with graphite anodes, relatively low cost, widely mass-produced. Lithium hexafluorophosphate remains unbeatable due to its overall performance. But lithium hexafluorophosphate has a fatal flaw. Extremely sensitive to moisture, even at room temperature, LiPF slowly decomposes. With even trace amounts of water, decomposition accelerates rapidly. Why this is bad? The consequences: shorter cycle life, increased internal resistance, electrolyte turns yellow or dark. Lithium salt is key to the electrolyte. Lithium hexafluorophosphate balanced and mainstream. Lithium bisfluorosulfonyl imide. Lithium bistrifluoromethanol imide stable but costly. Lithium perchlorate. Lithium hexafluoroarsenate risky choices. Lithium hexafluorophosphate is king. Effective LiPF concentration. As the concentration of LiPF increases, the viscosity of the electrolyte gradually increases. As the concentration of LiPF increases, the ionic conductivity of the electrolyte first increases and then decreases. Did you know? Electrolytes in lithium batteries contain additives tiny amounts, but huge impact. Unlike solvents or lithium salts, they're added in small amounts but precisely designed. Each additive plays a role. Unsaturated or cyclic compounds protect the anode, nitriles and sulfur-containing additives protect the cathode, and hydrates enhance thermal stability. Boron-based additives improve lead transport at low temperatures. Overcharge additives release gas to trigger protection. Flame retardants stop chain combustion, and fluorinated surfactants improve electrode wettability. Say additives help build a protective layer on the anode. They work at different voltages to form a stable film that improves battery life, lowers resistance, and helps performance in both hot and cold conditions. Common additives include VC, FEC, sulfur compounds, maleic anhydride, and special lithium salts like Libok. These ingredients make batteries safer and more durable. SAE additives help protect the cathode. They form a stable film, reduce side reactions, and stop metal ions from dissolving. There are different types. Nitrile compounds stick to the surface. Some additives form a protective layer by reacting on the cathode. Others, like sulfur, boron, or acid anhydrous, make the interface more stable, especially at high voltage. Some, like bisphenol, work through oxidation and polymerization. Nitrile additives can help protect the cathode by forming a stable layer. They also reduce cobalt dissolution during high-temperature storage. Boron-based additives bond with oxygen atoms on the surface, lowering their reactivity and helping prevent electrolyte breakdown. Electrolyte stabilizers help the battery last longer. Some block water and acid, others catch harmful particles. This keeps the electrolyte stable and the battery safe. Researchers are developing new additives, like lithium salt additives for solid-state batteries and interface modifiers for high-nickel cathodes. Electrolyte quality starts with tight control over raw material moisture, impurities, and mixing temperature. The industry focuses on 5 key parameters: moisture and HF content, conductivity and density, and color. We use electrochemical testers and precision analyzers to ensure every batch is stable and reliable. Mass-produced electrolyte is sealed in stainless steel drums with nitrogen-positive pressure, typically stored between 5 and 35 degrees Celsius. Electrolytes containing unstable additives need cold storage. Samples should avoid glass containers because they can produce toxic gases. Stainless steel and polymers like PP and TFE are preferred. Future electrolytes focus on expanding usable temperature ranges, improving safety with gel and solid-state options, and increasing high-voltage tolerance in line with cathode advances. Functional electrolytes are also being developed to meet the diverse demands of various applications.